Okay, guys, welcome to our first video podcast of the year. Probably the first of many to follow. Um, we've sort of overstuffed the lecture in terms of what I want to get in during those 50 minutes that we meet twice a week. And so what I'm going to do is use video podcasts as a way to finish out the chapters if we don't manage to complete within the allotted time during the week everything I want to talk about in the lecture. And there's a lot that I want to touch on, and I want to make sure that you get a chance to hear what I have to say about it so that you can use these video podcasts as a way to enhance your notes and as a way to reference some of the material in the book. So when last we left off, we were just finishing up the scientific method, and the reason that I wanted to touch on the scientific method as a keystone of science is that if properly carried out, the scientific method always brings you to eventually the truth of a situation, how a natural phenomena actually operates. And the reason for this is because experiments, when properly designed, will give you the data that are operational in the physical world. If you use bias, if you do not take note of the data that you generate, or if you favor certain data over others, what you're doing is introducing the human element into scientific research, and what that'll do is steer you away from the variables that are actually operating in the phenomena that you're examining. So we have to have rigorous application of the scientific method in order to get to the truth of a situation. And one of the things I wanted you to note when watching that scientific method video and when going through the steps of the scientific method is that the more variables that you have to examine in a particular phenomena, the more difficult it is for you to reach a valid conclusion, because you're going to multiply the number of experiments and the number of control groups that you're going to have to employ in order to get data that are meaningful. And this is one of the reasons that questions that are too broad in scope are really difficult to answer using classical applications of the scientific method. So a lot of times shortcuts are taken, and those shortcuts involve using certain assumptions in your observed data as baselines of comparison, and that can lead to erroneous conclusions. And we talked about the fact in lecture last week that, for instance, a lot of climate research that centers around the changing of the Earth's temperature over the past several millennia involve not so much looking at physical data, but at using things called computer models, which are based on assumptions that the researcher inputs into the model to use as a control. And when you're talking about the planet Earth, it's probably self-evident to you that a computer model and the actual planet Earth are not the same thing. And so when you try to draw conclusions based on computer modeling and extrapolate that to what's actually happening on the planet, very often you find wild disagreements. And this has been borne out in past predictions based on computer models that haven't held up. In order to accurately perform experiments related to things as broad in scope as climate change, what you literally have to have is a separate Earth that has exactly the same components as the Earth that we live on, except for the variable that you're examining. And if you were interested, for instance, in man-made influence on the global climate, what you'd have to have is a separate planet Earth without human beings on it. And it would have to have undergone the same geohistory, the same changes that our own planet has undergone, and then you could make a valid comparison. Until then, what you're doing is you're approximating anything that you're using when you're employing a computer model and the actual planet Earth. So you have to take a lot of these reports in the popular media and a lot of these reports that are published even in peer-reviewed journals with a grain of salt. And it's generally true that when you perform an experiment employing the scientific method, that the conclusions that you draw are generally much narrower than you would anticipate at the outset of the experiment. And I'll give you examples of that as we move on through these chapters in the book over these next 15 weeks. So let's talk a little bit about environmental science. The best hypotheses make predictions. These predictions provide a way to test the hypotheses. If the experiment refutes the hypothesis is rejected. And believe it or not, even at the highest level of science, there are scientists that fail in this step because they'll have a favored hypothesis, they'll have a bias, they'll have a pet theory that they want to be true. And very often what they'll do is they'll throw out data that refutes their hypothesis, and they'll only look at data that support it. And that's not an accurate application of the scientific method. Another thing that happens, believe it or not, is that sometimes data get altered in order to support a particular hypothesis, and that is out and out scientific fraud. And you wouldn't think that people that are nominated for Nobel Prizes or have extremely influential positions at various research institutes around the world would ever engage in such behavior, but you would be surprised. They do, in fact, let their human biases influence their interpretation of scientific data. And the reason for this, in part, is because of prestige and money that's involved in science. And it's very difficult to tease those elements away and engage in just pure scientific inquiry. If the hypothesis is verified repeatedly, the hypothesis is strong, it's supported. Remember that science progresses from uncertainty to less uncertainty, and so we never are completely positive about the natural world because there could always be an experiment that could fly in the face of our particular hypothesis and refute it. But generally speaking, the less uncertain we are, the closer we are to what you'd think of as a theory. Science is self-correcting even though it never proves anything. And I would say it never proves anything, but it gets very, very close to proving something. It'll approach the truth of a situation as more and more data are compiled to support a particular hypothesis and a particular theory. Environmental science employs experiments to test these hypotheses. The variables that are employed are factors that influence a process. In order to test a hypothesis, 2 experiments are carried out. The experimental group is where the chosen variable is altered in a known way by the experimenter. And this is very important. This is very different from simply comparing sets of observations in the natural world. When you're performing an experiment on the bench, you're able to carefully control the variable that you're testing, and as a result, the data that you produce are going to be much more valuable, much more rigid, and much more indicative of the phenomena that you're examining. The control group is where the chosen variable is not changed, and you always have to have a control group in your experiment in order for your experiment to mean anything. The data that you generate from your experimental group do not have meaning unless the control group with the unaltered variables is used as a baseline. And let's go back to our example of climate change. One of the assertions made in a lot of environmental science textbooks and in popular media today is that human activity is primarily responsible for global climate change. And in order to assert that with complete certainty, what you'd have to have is a separate Earth without mankind on it in order to examine whether or not human activity is in fact the major contributor to climate change. Because then you'd be subtracting out the one variable that you're claiming is responsible for the phenomena that you're seeing, and that's humans and human activity. So in lieu of that, what you have to use are computer models, and again, those models, since they're based on assumptions, do not always necessarily represent the best control group. We can ask, what is the difference in any between these two groups? Any differences should be due to the experimental variable, if done properly. Scientific theory is an integrated explanation of many hypotheses, each supported by many observations and experiments, and this simplifies and clarifies our understanding of the natural world, and it provides a solid ground of science. Scientific theories are generally accepted as true or having a broad ability to explain natural phenomena, even though in science we never get to complete and absolute truth. Contrast this with the general public's use of a theory as a guess or a hypothesis. So these two popular conceptions of theory are often conflated in the popular media, and in science a theory has a very rigid definition. Let's take a look. Science is constantly evolving, as is everything. As new evidence comes to light, conclusions may change, and therefore scientific conclusions are provisional, which doesn't mean they're invalid. They just explain our understanding of the data at that particular point in time. And as new data come to light, we often have to change the prevailing theories, the prevailing hypotheses, because it only takes one experiment that produces data in contradistinction to what's gone before to cause a big change in what was heretofore accepted as a complete hypothesis and a solid theory. Examples: smoking and cancer. I'm sure that you've heard in the popular media, and maybe you've read in your textbooks or in peer-reviewed journals, that smoking causes cancer. Now, what I'll tell you is probably something you haven't heard before, but that evidence is correlative. And there's a very big difference between correlation and causality. Correlative evidence is evidence in which the occurrence of one particular phenomena coincides with the occurrence of a second phenomena. It does not necessarily provide a causal link, a cause and effect relationship, whereas causality shows a mechanism whereby one phenomena produces the second phenomena. I'll give you an example. If you were to pick up a rock off the ground and then you were to let it go, drop it, it would fall to the ground. And you would find that that would happen every single time you let go of a rock and it fell to the ground. And the reason for this is that the force of gravity acting on the mass of the rock causes it to accelerate towards the Earth's surface with a specific acceleration rate, that being little g. And this would happen every single time you dropped that rock. And the reason for that is that there's a cause and effect relationship. The mechanism whereby that rock falls to the surface of the Earth is gravity. That is the operating phenomena. And so every single time that occurs, the other thing will follow. And that's been demonstrated not just on Earth, it's been demonstrated on the Moon, it's been demonstrated in any number of different scenarios. Now, there's a lot about gravity that we don't understand, but we do know that this force operates on objects that occupy space and have mass. Now, correlative evidence is simply a coincidence of two events, and it doesn't necessarily imply that one causes the other. Let's take a couple of examples. Every day that you've awoken, gotten out of bed, the sun has come up. Very high correlation between those two events. However, does that necessarily imply that you getting out of bed causes the sun to come up? And the answer would be no, because there's no cause and effect relationship. There's no demonstrated mechanism that indicates that one is going to cause the other to happen. And the difference here is you do not have a demonstrated model whereby the two events are causally linked. Smoking and cancer is another perfect example. You've probably read in the popular media, as we previously stated, that smoking causes cancer. This evidence is correlative. This means that there's a higher incidence of cancer among people that smoke. Now, if you think about it, there are a couple of different ways that that data could be explained. The first way that the data could be explained, and the popular interpretation of that data, is that there's something in cigarette smoke that increases the incidence of cancer in individuals who smoke. And that's certainly a reasonable interpretation of the data. But there's another interpretation of the data that would also fit those numbers. And it could be that people that are predisposed to cancer for some other reason happen to engage in smoking more frequently than people who aren't. And that data would still match up. Now, that's not a likely explanation, but that's an explanation that fits the data. Let's give you another example. It can be demonstrated that in any given community, the more churches that are present in that particular community, the higher the number of crimes that are committed per year. And so one interpretation of that data is religion causes crime, and that's one possible explanation. But if you look deeper into that data, what you find is that there's another variable that tends to track with those two particular pieces of data, and that variable is population. The higher the population of a particular community, the more churches that you have, and the higher crime rate that you have. So that might be a more reasonable explanation for those particular data. So you have to take correlative evidence with a grain of salt. All a correlation is a correlation. It does not necessitate a link. Not until you can demonstrate that you have 100% correlation between one event and another event. And that's often very difficult to do. It takes a lot of testing and experimenting in order to arrive at that particular state, to actually find the mechanism that links the two up with 100% certainty. In correlative data, what you find generally is something shy of 100% certainty, and so you can certainly say that this evidence is supportive, but it is not conclusive. And so this is one of the things we want to be aware of when we look at a lot of the data in your textbook, in the popular media, and even in the data that I've provided on Blackboard in the journal articles section of the course. You want to read that, and you want to look at the data as they are, okay, and understand the difference between correlation and causality. And if you're unclear about that, come to me during office hours and we can examine this in a little bit more detail. Okay, so next thing we want to look at is a couple of concept checks. What is environmental science, and what are some of the disciplines involved in environmental science? Environmental science is the interdisciplinary study of humanity's relationship with other organisms and the physical environment. Some of the disciplines involved in environmental science include ecology, atmospheric science, environmental chemistry, geology, and physical geology. What are the 5 steps of the scientific method, and why is each important? Boy, this is a big question right here. This is something, if you don't take anything else away from this class, I want you to take away a solid understanding of the scientific method and how it works. The 5 steps of the scientific method include recognizing a question or an unexplained occurrence in the natural world, developing a hypothesis or an educated guess to explain the problem, designing and performing an experiment to test that hypothesis, analyzing and interpreting the data to reach a conclusion, and sharing the new knowledge with the scientific community for evaluation. Each step is important because they create a standard by which to prove and disprove hypotheses worldwide. Use of the scientific method contributes to the ability of researchers worldwide to discuss and share scientific knowledge. And you really do a disservice to science in general if you purport to have rigorously examined a phenomena using the scientific method and you have in fact either included data that are fraudulent or have not adequately analyzed the data that you have, and you've drawn conclusions that are not valid based on your experiments. Because what you do there is you cripple the body of knowledge, and science builds on previous knowledge in order to arrive at a theory that can broadly explain a lot of different phenomena in the natural world. And so you're really committing a crime against knowledge if you let your own bias creep in to your raw data. And eventually that will be found out, because one of the things that you do in science is you attempt to repeat the experiments of other individuals, and it's the ability to reproduce those data under the same conditions that indicates that your experimental design was sound and your conclusions were valid. And if you don't do that, what will happen is you'll be found out. Eventually what will happen is somebody will attempt to repeat what you've done. They won't be able to reproduce it, and then we'll have a controversy. And there are a lot of controversies in science right now. You could probably, it would be difficult for you to find a current scientific hypothesis that is not contested in some fashion or form by data that seems to run in contradistinction to data generated by other groups. And so science, again, is a constantly evolving thing. But you have a big responsibility as a scientist to be truthful and to be objective, and that's very difficult often for human beings to do. Okay, so let's talk a little bit about how we handle environmental problems. Our learning objective will be to list and briefly describe the 5 stages of solving environmental problems, and here you can see an example of this flow chart. So we start up here in the corner where we define the problem, we test hypotheses, and we generate models to show how the present situation developed and predict the future course of events. Now again, this is probably the most important part of this entire flow chart for environmental science. If you don't do this part right, and you generate data that are inaccurate or are colored by your own biases, you're going to set into motion a whole series of events that could end up being extremely detrimental to a lot of different aspects of human life. Next step is risk analysis. So we look at the potential effects of various interventions, and which include doing nothing, and we analyze them to determine the risks associated with each particular course of action. This is a huge undertaking, because if you're wrong in step 1, and then you propose that we have to engage in some massive effort to change a particular situation, which can be extremely costly, and it turns out that you were wrong at step 1, what could happen? Well, you could end up wasting all kinds of economic resources trying to fix something that didn't need to be fixed in the first place. Next is public engagement. We change the public attitudes, and this involves explaining the problem, presenting available alternatives for action, and revealing probable risks, results, and the cost of each choice. And again, this harkens back to the previous 2 steps, the risk analysis and the scientific assessment. Again, if you do step 1 wrong, steps 2 and 3 are going to be way off base. And then next we have political considerations. Elected officials, often at the urging of their constituencies, implement a course of action based on scientific evidence as well as economic and social considerations. And then finally we have long-term environmental management, where the results of any action taken should be carefully monitored to see if the environmental problem addressed is being ameliorated, is being improved. But again, you can see that if we don't perform step 1 accurately, if we don't generate meaningful data that are not colored by bias, then what happens is we set into motion a whole series of events that can be extremely damaging. So the person on the bench has a big responsibility here. Okay, so let's take a look. Another concept check. What are the 5 steps used to solve an environmental problem. And those are scientific assessment, risk analysis, public engagement, political considerations, and then long-term environmental management. Okay, so here we're looking at a nuclear power plant, and in the back of Chapter 1 it talks about a couple of important social phenomena which are not in my backyard and not in my term of office, where what happens is that the public's perception of a particular environmental problem can be affected by coverage in the popular media, and as a result, politicians who respond to their constituencies will not engage in policies designed to ameliorate a particular environmental problem because it'll put their reelection efforts at risk. And so the phenomena here is obviously disposal of nuclear waste, and the idea is that nuclear energy, which is a very clean form of energy, involves using nuclear reactions to heat water, which generates steam, which turns turbines, which are big magnets on wheels that spin around copper coils and generate electricity, provide a lot of very clean energy for a wide number of communities. Most of Western Europe uses nuclear energy to supply their electrical needs, and as a result they don't have as high a demand on sources such as coal and oil, which can be used for other purposes. But obviously the radioactive waste causes a lot of concern, because radioactive waste, if disposed of in an improper manner, can produce environmental consequences such as mutation and massive environmental damage. So it's incumbent on people that run nuclear power plants to dispose of the nuclear waste in a way that doesn't put the public at risk. And there have been a couple of incidents, Chernobyl being one and 3 Mile Island being another, in which nuclear waste ended up contaminating the local environment due to faulty engineering practices and improper operation of the facility. And so the problem of what to do with nuclear waste is a growing concern in communities that employ that type of power generation, and nobody wants it in their backyard. They're afraid of contamination. They're afraid of the risks to their own lives and their own well-being. And so what happens is that the nuclear waste tends to stay where it's generated, which is not a tenable solution, because eventually it's going to build to the point where it won't be able to be properly contained. And so the U.S. government initially was looking at a lot of different sites for nuclear waste disposal, but due to political concerns, only one, Yucca Mountain in Nevada, was considered as a long-term solution. And obviously the residents in Nevada were upset about that. And so what's happened now is that these efforts to dispose of nuclear waste have stalled, and as a result the problem continues to exacerbate itself. So just something to consider. So this is just to tell you, NIMBY, not in my backyard, and NIMTOO, not in my term of office. Examples: people don't want power plants, landfills, or incinerators nearby, and politicians want to be reelected, so they don't support those decisions in their district. And as a result, what happens is that the waste problem exacerbates itself. And so it's incumbent on us to come up with a solution that will satisfy everyone's concerns, and part of that comes with educating the public, which can be a big challenge. Okay, we've come to the end of our first podcast, and I'm certain we'll have more to come. Chapter 2 starts next week, and I'll see everybody Tuesday, so have a nice weekend.